Okay, lesson 1. Part of this is the same lesson 1 that I taught to pre-cal, real numbers. Just helping us review, okay, what are the different types of numbers, and all of that. But just a lot of different, math review. So I'll be honest, I don't remember when we actually start doing calculus, but we won't actually technically do any calculus this week. Okay, it's all just review type stuff. So it's algebra type stuff, maybe some pre-cal thrown in. Now, does that mean it's as easy as what it was in Algebra 2? No. Okay, you're going to have to work with me, okay? I'll be honest. I'm not saying it's going to be easy. It's going to require some work, but we'll make it. Okay, so up at the top is kind of a diagram there. Real numbers. So if you recall, everything we work with, for the most part, falls into the real number category, or falls under the real number umbrella, except imaginary numbers, which I'm trying to think if we ever use imaginary numbers in calculus. I'm not sure that we do. I'm really, we use them a little bit in pre-cal, right? Not a ton, but we use them a little bit in pre-cal, but we don't really talk imaginary numbers. So everything falls under the real number umbrella here. Now, I guess the one thing I will say here, real numbers, not imaginary is the point. Now, if everything falls under the real number umbrella, all real numbers are either rational numbers or irrational numbers. What do you remember about rational and irrational? So all reals are either rational or irrational. What do you remember? Okay, a decimal that does not repeat or terminate. That's what I kind of like to use as my definition. So I'm going to say a non-terminating, non-repeating decimals. I kind of abbreviated there because there's not a ton of room, but just throw in something there to kind of remind yourself. What are examples of irrational numbers? Pi. We don't call it epsilon, we just call it e. But it is. We call it the natural number. It's e. And then the other thing that often falls into the irrational number category, certain square roots, such as square root of 3. That's a random one I picked. Not all square roots fall there, right? Because square roots that are perfect squares are going to go over to the rational side. Okay, so irrational numbers. Non-ending, non-repeating decimals. My non-math definition is big, long, messy decimals. That's that's the non-math part of me. Okay, so then rational numbers. What are rational numbers? Okay, decimals that repeat or terminate. They can all be expressed as what? Yeah. They can all be expressed as fractions or ratios. Officially, if you look up a definition for rational numbers, it will say numbers that can be expressed as the ratio of two numbers. Fancy word for fractions. Now, I guess I'm forgetting here. There are, fancy letters that we use to represent this. And so in the book, you will see them talking about various subsets. And if you see a fancy R, can you see that? Basically, it's an R, but there's two vertical pieces instead of just one. That fancy R stands for real numbers. So, if you see that, this number is a member of or this answer is a member of the real numbers, they might use that fancy R to indicate real numbers. Now, there's not a letter to represent irrational numbers. But for rational, notice we've already used R. I don't know what the connection is, but they use Q. And the fancy part of Q, I don't know if you guys can see that, is there's a vertical line on the left, within the left side there. I don't know how well you can see that. But that fancy Q represents rational numbers. And I'm not going to say that we're using them a ton, but they're good to know know what they mean. Okay, integers. Remember what integers are? Okay, positive and negative whole numbers. Technically, you have to know what a whole number is, but I get it. That's what I say too. I'm going to write ... -3, -2, -1, 0, 1, 2, 3, ... I agree. Positive and negative whole numbers. And to represent the set of integers, they use a fancy Z. And the double is down the middle. Okay? So integers are Z. And keep in mind as we're doing this, okay? We start with real. Rationals fall under real, correct? And then notice integers, all integers fall under rational, because all integers are rationals. Now, we already used the word whole numbers. What do we mean whole numbers? Okay, the positive ones? What about 0? Do I include 0? For whole numbers, yes. So, whole numbers are 0, 1, 2, 3, so on and so forth. I don't believe there's a letter to represent whole numbers, unless I'm forgetting one. But I don't have one written down. Okay. And then what are natural numbers? Okay, basically take off its whole numbers minus the 0. So 1, 2, 3, so on and so forth. And to represent natural numbers, we use what I call a fancy N. The doubled up leg is the left leg. That's why. Okay. Q being rational was because a rational number is a quotient. So Q for quotient. I knew there was something. I couldn't remember what it was. But yeah. Okay. So, anyways, just kind of real numbers there. Now, for set notation. Okay. Natural numbers, yes? They're a part of whole numbers. Whole numbers are part of integers. Integers are part of rationals. Rationals are part of reals. Fancy set notation that you might see. The natural numbers are a subset of the integers, which are a subset of the rationals, which are a subset, oops, you can't see what I'm writing, sorry, of the reals. And so that little sideways U is what it looks like, almost like a C, but it's like a sideways U, means is a subset. Again, this is just so you can be familiar with notation in case you run into it. It's not that you run into that often, but you need to be familiar. So, in easy terms, this is saying, okay, natural numbers are part of the integers. Integers are part of the rationals. Rationals are part of the reals. Okay, fancy terminology. The natural numbers are a subset of the integers, which are a subset of the rationals, which are a subset of the reals. Okay? Okay. Not that you're doing a whole lot with it, but just make you familiar. The R for reals, you'll probably see that most often and use that most often, which that's an easy one to know. So. Okay, I'm not going to really write anything down for most of these down below, but just kind of run through, there's some basic properties. My honest opinion is you probably use all these properties, have used all these properties before, but you don't necessarily know what they're called or know that they're even a property. Okay, you know them kind of internally. Okay, so the first one there, well, this is where I have to go over what it says, isn't it? Trichotomy. One of the following, so basically given two numbers, one of the following must always be true. Either x equals y, x is greater than y, or x is less than y. Okay, that's called the trichotomy. That's pretty much self-explanatory though, isn't it? Given two numbers, they're either equal, the first one's bigger or the second one's bigger. Okay, transitivity. Somewhere maybe back in middle school you had the transitive property, maybe even back in Algebra 1. If x equals y and y equals z, then x equals z. So basically if two things equal y, they have to equal each other. That's the transitive property. Addition property. If x equals y, then x plus a equals y plus a. So basically if x equals y and you add a to both pieces, they're still equal. Kind of common sense in a way. You just don't think about it this way. Multiplication property, very similar. If x equals y, then xa equals ya. So if x equals y, then x times a is the same as x or y times a. Reciprocal property. If x equals y, then 1 over x has to equal 1 over y. Closure laws. If that says x and, that's an and sign. If x and y are in a set, then so are x plus y and x times y. So if x and y belong to a certain set of numbers, say the whole numbers, then that means if you add them, x plus y, you still get a whole number. And if you multiply them, you still get a whole number. Okay? Now, that does not stay true for subtraction and division. That only stays true for multiplication and addition. Okay? Commutative property, I'm taking you back to middle school, maybe even elementary days. I didn't realize they learned these properties in elementary until my kids went through it. But my kids have been taught the Natalie's just 6th grade. She's been taught commutative property. So x plus y equals y plus x. Doesn't matter if you add 2 plus 3 or 3 plus 2. Associative property. It says if you're adding or multiplying 3 pieces, it doesn't matter which 2 you add or multiply first. So it could be x plus y plus z, so y plus z would be added first in parentheses, or you can move those parentheses and say x plus y and then plus z. Distributive property. That's an old one, right? X times y plus z means x has to distribute. You have to do x times y and x times z. So x times y plus xy plus xz. Whenever we talk about an identity is what can you do to something to get it to stay the same. So in addition, what's the identity? What do you do to something to keep it the same? You add 0. So in addition, the identity is 0. In multiplication, what do you multiply something by to get it to stay the same? 1. So the identity in multiplication is 1. And then inverses. So inverses is how do we get the identity? In terms of addition, how do you get 0? You add a number and its opposite, or negative. In terms of multiplication, how do you get the identity of 1? Well, you multiply a number. Now, they have it written as a number times x to the negative first power. But that's probably not how you really think about it. How do you multiply to get 1? A number times, I would say it's reciprocal. That's like saying, okay, I'm going to do 2 times 1 over 2, and I'll get 1. That's the same thing as saying x to the negative first, though. Okay. That all sounds a little familiar somehow or another, doesn't it? Again, maybe you don't know the names, maybe you don't think about them as properties, but you use them. Okay, let's do some fancy math then. Okay, this is technically an Algebra 1 problem. Maybe I should call it Algebra 2, because it's definitely a step up. Solve y equals v times the quantity a over x plus b over mc for c. Okay? Not a favorite skill to begin with. And then on top of it, this is not a pretty problem, is it? Okay, so our goal is to take this mess and to make it C equals. I'll tell you up front, there's not necessarily one right way to do this. There are multiple different directions you could go to, just depends on who you are and how you want to do this. Thoughts on getting started? Okay, distribute the V. And honestly, it comes down to it's going to be ugly no matter what we do here. So the other option would be to divide the V over to the Y. It's not necessarily any prettier. You go with what's most comfortable. So, chair's stuck here. If we distribute the V, okay, then I'm going to have Y equals, when I say V times A over X, I'm going to write it as VA over X. Is that okay? Plus VB over MC. I don't know why. Normally I would have said AV and BV, but I didn't. Okay. A couple different directions we could go here. Notice, where is C? In the denominator. How do we get rid of a denominator so we don't have to work with all these denominators? How do we clear out the denominators? Yeah. What are all the pieces that are in the denominator? Agree? There's an X, an MC, and the common denominator between X and MC is just going to be XMC. So one option here is to take both sides of this equation and multiply by XMC, or whatever you want to call that. Okay, and we did that by, common denominator, X and MC, multiply them together, common denominator. So, on the left, what is XMC times Y? Okay, YXMC, I was going to say XMCY. Some combination of those four pieces put together, correct? Okay, VA over X times XMC. What happens there? X will cancel, and we're going to be left with VAMC, or whatever combination you write. Plus, next part, VB over MC times XMC. Yeah, MC will cancel, so VBX. Okay, thoughts?
So now we're going to need to, this is the order I would do it, subtract over the VBX, and then there's a C on the other side too.
There's C's on both sides right now, aren't there? Yeah. I would say if you were just looking at this C, weren't you? Yeah. Since there's C's on both sides, can we get those C's on the same side at least? So in order to get those C's on the same side, I would subtract the VAMC over to join the XMCY. It's like alphabet soup here, isn't it? So I'm going to say XMCY minus VAMC, and that equals VBX. Is that okay for you guys? Other than you're like, really? This is ugly? It's not about are you okay with the ugliness of this problem. It's, don't let me do a step and lose you. Speak up right away. I don't know I know what I want to do here, but I don't know if you guys, both terms have C, right? What can I do with that C, since both terms have yeah, I started to say both terms have a common factor. They have a common factor of C, so what I'm going to suggest is factor the C out front. Once we factor that C out front, what remains? Okay, what he said. Factor the C out, and then I have XMY minus VAM in parentheses equals VBX on the right. And then since it's C times that factor in parentheses, you can divide by that whole thing and say C equals VBX over, and it's AM. Now right there, that doesn't even technically match what's in my answer key because my letters are in different orders. But, okay. Part of the point of that problem, folks, you can't let working with a bunch of letters intimidate you. Okay? That's no different than if we'd worked with a bunch of numbers in there, or numbers and letters mixed in. That was a bunch of letters, but it's, it's doable, isn't it? Not pretty, but doable. So that's, again, that was all algebra skills.
Honestly, I think because I took physics last year, that wasn't so bad. Because a lot of physics was a pure.
That you had to do that. Okay. We've got, on 1.2, we've got an A and a B here, and we're going to simplify this. Now, let me state, there's certain things that keep coming back over and over throughout this year, and there's certain things that we do like once, you don't see a whole bunch more. This is one where it comes back, okay? So just looking at example A right now, you've got X over A plus M over 1 plus C over D. So you've got lots of fractions within fractions. Our job is to simplify it. Not that it's going to look pretty when we get done. However, is it properly fractions within fractions within fractions in this mess? No, not at all. So I'm always going to say, okay, take the most inside denominator. Okay, so like if we get all the way down to the bottom here, we have a D, right? Which D is just D. But start with the 1 plus C over D. And I'm going to tell you to add those together and simplify them. Can you add 1 plus C over D and then simplify it? Because we're going to keep doing that process of add and simplify over and over is what I'm going to keep taking you through. So that's what we're starting with right here. So we're going to add and simplify. Now the question becomes, how do we add 1 plus C over D? If you want to find a spot to put this in your notes, you can. What has to be true of 1? Well, it's 1 over 1. And so 1 over 1 could be D over D. Are you seeing this? I'll be honest, I usually do this part in my head. But I know we need the visual to get us started here, don't we? Okay, so 1 plus C over D is really going to be D plus C over D, or D plus C over D. Can you follow this step if I put it up here? And again, if you're going to need that later, find a spot to write it down. Okay, so what I'm going to say is that I'm going to come over here, and we have X on top, right? Over, we have A plus M over, what am I replacing 1 plus C over D with? D plus C over D. Okay, so that right there got replaced there, didn't it? So what we've done so far is we added. We added 1 plus C over D. Now, we have a fraction within a fraction here, yes? How do we do M divided by D plus C over D? It shows, tell me you can't see what I'm writing. I guess you couldn't see, it wasn't that much I'd cut off, but. So the part I'm working on right now is this part right here. We added, and now we've got to simplify that part. So we need to do M divided by D plus C over D. Okay, so think dividing fractions. How do we divide? It's m divided by d plus c over d. How do we divide when fractions are involved? Multiply by the reciprocal. Keep, change, flip is what a lot of you say. So then it's m times d over d plus c. And all of this time, what is m as a fraction? M over 1. So then when I multiply, this becomes md over d plus c. And again, I'm not really writing that step in the notes, but you might want to write it down in the notes, right? Because you have to be able to recreate this in homework. So, okay, so continuing along, I still have a big old X on top, don't I? I still have A plus, and now I'm going to rewrite it as MD over D plus C. Okay, so we took 1 plus C over D, we added it, and then we simplified it with the numerator it was under. Now, repeat the process. Now we've got to do A plus MD over D plus C. So now we're going to add and simplify again. So if nothing else, you know that on top is still going to be X. Debating what's the... So what are we doing here? We're adding A plus MD over D plus C. How do we make A a fraction? A over 1. What's my common denominator got to be? D plus C. So what do I do here? Multiply by D plus C, right? So on top, it's going to be A times D plus C. I guess if you want, is it better if I put the 1 there, or is that worse? It was A over 1, and I'm trying to get the common denominator of D plus C, so I multiply numerator and denominator by D plus C. Common denominator is D plus C. My numerator, how close am I to the end? We can do it a couple different ways. We can leave it as is, as A times D plus C plus MD, or we can distribute it out. I actually left mine. And it's fine either way. If you want to write it as AD plus AC plus MD, you can. Kind of like that better, honestly. AD plus AC plus MD. I know why I didn't do that, so it would be easier following here, I bet. So that's my new denominator now, right? AD plus AC plus MD all over D plus C. Okay, we're almost there. We have a fraction within a fraction. How do we divide fractions? Multiply by the reciprocal. Do it without me writing it up here or not? It's X divided by AD plus AC plus MD over D plus C. What is X as a fraction? X over 1. Right now it's divided by AD plus AC plus MD over D plus C, but we need to keep, change, flip. So So now it's going to be D plus C over AD plus AC plus MD. Multiply this together. You can say X times D plus C over AD plus AC plus MD. And you can leave it as X times D plus C. Or you could write the XD plus XC over AD plus AC plus MD. This is one of those ones, equivalent forms. There's going to be lots of equivalent forms. Because my answer key I was going off of, I had X times D plus C over A times D plus C plus DM. Okay. These type of problems, folks, whether it's in variables, whether it's in numbers, I'm going to tell you from the beginning. Do not just let them go and think, I think I'm just going to skip that topic and not try and figure it out. It's not a topic you want to do that with, okay? Keep working at it. I'm not saying you're going to master it day one, but keep working at it. But technically, guys, that was all algebra. Crazy big algebra, but it was algebra. Okay, B. B is a slightly different setup. We have fractions being added together and then divided. My recommendation is you add the fractions in the top, add the fractions in the bottom, then you have a fraction divided by a fraction. Can you deal with a fraction divided by a fraction? That's what we just did a bunch, right? So what common denominator would you like on top? On the numerator of the whole thing, that is. We can go smaller than x cubed. Because x and x squared share an x. So they share an x. And then there's one x left over, so we can actually just use x squared. Right. Because if we're using x squared, a over x squared stays, right? How do you make x become x squared? You multiply by x, which what's that mean you have to do to b? Multiply by x as well. And so then, both denominators are x squareds, right? So what's my numerator if I add? A plus bx. I promise it's algebra. Okay, what about my denominators? Current denominators are x squared and xc. What's a common denominator? Yeah, there's one x in common, but this one has two x's. Remember, you always go with the higher exponent, basically. So there's an x squared and a c. So denominator x squared c. What do we have to multiply the m by? To get that common denominator, we multiply by c. C times m, mc. Plus, what do we have to multiply the k by? What is it missing? It has x and c as a denominator. It needs another x. And so k times x is kx. Now we should be getting into your ballpark. Maybe we've already been there, but for those of you that are dying right now, fraction divided by fraction, folks. Keep. So I'm going to keep a plus bx over x squared. Change. I'm changing division to multiplication. And then I'm going to flip. So x squared c over mc plus kx. Does anything cancel? X squared is this denominator. X squared is a factor of x squared c. Sorry guys, I'll get that in a moment. So my x squared, a plus bx would have to have another a plus bx to cancel. mc plus k plus kx. So nothing else cancels. Put it all together as one answer. Sorry, the computer's being a little slow and coming back here. Oof. So I'm going to write C times A plus BX, and I left my A plus BX in parentheses, and my denominator, MC plus KX. You can leave it like that. Now, is it wrong if on top you said AC plus BCX or something? No, you can distribute that up top. It's whatever. There's no right or wrong, so to speak. Okay. We gotta pick up the pace here. We've got a lot to do yet, and not as much time. Good news is, this next one shouldn't be as bad. Okay, radicals. 4 plus square root of 2 over 3 minus 2 radical 2. What's wrong with this? Okay, can't have radicals in the denominator. How do we get rid of that radical in the denominator? We're going to rationalize. And how do we rationalize? What are we going to multiply by? Ooh, good word. The conjugate. Remember that word? What is the conjugate of 3 minus 2 radical 2? 3 plus 2 radical 2. What you do to the denominator? You must also do to the numerator. So we're multiplying numerator and denominator by 3 plus 2 radical 2. How are we going to multiply these guys? What's that F word? We are foiling. Okay. So 4 times 3. I'll take this one. 12. Okay. Outsides. 4 times 2 radical 2. You guys can have this one. 4 times 2 radical 2. How about 8 radical 2? Whole numbers times whole numbers, radicals times radicals. So 4 times 2 is 8, radical 2 tags along. Okay, insides. What's radical 2 times 3? 3 radical 2. Whole number 3 times square root of 2 is 3 square root of 2. Okay, last one. Square root of 2 times 2 square root of 2. I'll go with 4. There's an outside 2 that's a 2, yes. What's square root of 2 times square root of 2? It's 2. Or it's square root of 4, which is 2. So square root of 2 times square root of 2 is 2 times the other 2 that's there makes it 4. Are we okay with that? That's basic math that you've just got to be strong at. Okay, denominator. First is 3 times 3, which is 9. What's the whole point of multiplying conjugates? The outsides and insides are going to cancel. So can I skip those? I would. Last, negative 2 square root of 2 times positive 2 square root of 2. Well, negative times positive is negative. 2 square root of 2 times 2 square root of 2. It is 8. Because there were 2's outside, right? The 2's outside are 2 times 2, so we already have 4 outside. Square root of 2 times square root of 2 is 2. Times the 4 we already had is 8. Well, 9 minus 8 is 1, so my denominator is 1, which means I don't even have to write it. Numerator cleans up to be... Yep, I just wrote it as 16 plus 11 square root of 2. Whole number is 12 plus 4 is 16. And then it's like adding x's. If they have the same variable, you can add them. If they have the same radical, you can add them. So 8 square root of 2 plus 3 square root of 2 is 11 square root of 2. Was that a little bit better for you? you're really hating me over the first one, the previous one. Okay, example 1.4 then. 3 square root of 3 halves minus 4 square root of 2/3 minus square root of 24. Okay, last time we couldn't have radicals in the denominator, so we had to rationalize. This time, you technically can't have fractions under a radical. So this time it's more rationalizing, how do we get rid of a 2 in the denominator? How do you get rid of a square root of 2 in the denominator? How do you rationalize that out? Doesn't have to be negative. You just multiply by itself, square root of 2. If I multiply that denominator by square root of 2, you've got to multiply the numerator by square root of 2, yes? We'll go back for the other parts in a moment. So I've already got the 3 out front. On top, what's square root of 3 times square root of 2? Well, square root of 3 times square root of 2 is square root of 6. They're both under radicals, so you can multiply them. 3 times 2 is 6. Denominator, square root of 2 times square root of 2. 2. I'm not working with this yet. I'm just working on this one. Square root of 2 times square root of 2 is 2. Square root of 3 times square root of 2 is 6. And the 3 I put up out front. Okay, so think of this. I wrote it as 3 square root of 6 over 2. It's also, you could think of it as 3 halves square root of 2. Or, excuse me, square root of 6. So you could write this as a 3 halves out front of square root of 6. Whichever one floats your boat there. Okay, minus. What do I need here? I have a square root of 3. How do I get rid of a square root of 3 in the denominator? Multiply by square root of 3. If I multiply the denominator by square root of 3, I multiply the numerator by square root of 3. Out front, I already have a 4. Numerator, what's square root of 2 times square root of 3? Square root of 6. Denominator, what's square root of 3 times square root of 3? 3. So I wrote it as 4 square root of 6 over 3. You could also think of it as 4/3 square root of 6. Minus square root of 24. We don't have to rationalize, but what do you know about square root of 24? Okay. Yep. 2 square root of 6. Did everyone get there? 24 is 4 times 6. Take out the perfect square. Okay. Which, if we want a denominator there, that's technically all over a denominator of 1. And why am I putting a denominator there? Yeah, we have to subtract all these guys. Now, can we subtract them? They all end up being radical 6s. So yes, you can. Basically, what you have to subtract is there's a 3 halves minus a 4/3 minus a 2. My recommendation here, what's the common denominator? 6. Let's put these all over 6, and that, to me, will make life much better. As good as it can get when you're working with fractions and radicals all at once. Okay, first one, denominator was 2. To make it 6, we're going to multiply by 3. And so out front, there was already a 3. 3 times 3 is going to be 9. So 9 square root of 6 over 6. Basically, 3 halves became 9/6. 4/3. The 3 had to multiply by 2, so the 4 multiplies by 2. 8 square root of 6 over 6, or in other words, 8/6. Yeah, it was 2 over 1. We're multiplying by 6, so it becomes 2 times 6, which is 12. Square root of 6 over 6. Okay, almost there. 9/6 minus 8/6 minus 12/6. Yeah. 9 minus 8 is 1. 1 minus 12, negative 11. So I've got negative 11 Square root of 6 stays along, denominator of 6 stays along. So that cleans up to be negative 11 square root of 6 all over 6. Or if you prefer, you could call it negative 11 sixths square root of 6. Okay. Example 5. We've got exponents. As we think about these exponents, this is a big old nasty exponent rule review is what this is. And I don't use the word nasty lightly because I don't know a better word for this. Okay, notice there's y's on top, there's a y on bottom. There's a z on top, z on bottom. If the bases are the same, how do we deal with exponents here? Okay, if they're dividing, you subtract, right? What about these two y's that are multiplying? Technically, you would add their exponents and then subtract these exponents. The z's you will subtract. And so you kind of got to think of this as two different pieces here. We've got a y piece and we've got a z piece. So if I look at y's, my powers on my y's, there's an x plus 3, right? The y right next to it, we're going to add those exponents. So keeping the base of y, I'm going to add x over 2 minus 1. And then what do I have to do? Okay, so we're going to subtract by the x minus a over 2. Now, what if I say x minus a over 2? Are you okay if I say that's x over 2 minus a over 2? So what happens when I subtract that? It's going to be subtracting x over 2. Subtracting minus a over 2 really says we're going to be adding a over 2. Okay, that's all my y exponent. We're going to clean it up here in a moment, but let's get our z exponent. What's my z exponent? We've got the a on top, and then what are we doing with the stuff on bottom? We're going to subtract. So I'm going to subtract the x minus a over 3. But can I go ahead and break that like I did the other one? Yep, we're going to subtract. It's going to be minus x over 3. And then it's really going to be minus negative a over 3, which really makes it plus a over 3. Okay, that is hard to tell, but there's a y and a z, and all the rest is exponents. Is that what you understand it to be? Okay, so let's clean up the y. What do we have going on here? What do you notice about this x over 2? Plus x over 2 and minus x over 2 cancel. 3 minus 1 is 2. So I see as my exponent, there's an x plus a 2, because 3 minus 1 is 2, and plus a over 2. It's not pretty, but it's a little prettier. Is that a good description? There you go. Okay, z. We have a 1a and an a over 3. So a over 3 is like thinking 1/3 a. So we have a 1a plus a 1/3 a. Or what's 1 plus a third? 1 1/3, which improperly becomes 4/3. Or yes, think 3a over 3 plus 1a over 3 becomes 4a over 3 minus x over 3. I don't know how much you can tell my y and z are the bases. It didn't turn out perfectly. Okay, I am running out of time. I have like 3 minutes left to go. You remember these radicals? If it's a square root, that is an index of what? A 2. That next one, it looks like, is a cube root. So what if I just real quickly tell you that this is, you see the x to the 3/4, right? Then there's x, the square root of xy. So I would think of that as the square root of x, which is x to the 1/2, times the square root of y, which is y to the 1/2. Then we have the cube root of x to the 4th. Oh, wait. There's another x to the 1/2 in there, isn't there? And then we have the cube root of x to the 4th, which is x to the 4/3. Right? The index is your denominator. And you would put that together. You would have to get your common denominators and put that together. I will tell you, it's x to the 37/12, y to the 1/2. You're adding your exponents, right?
That's getting back to the stuff we kind of
yeah. I really need to do some of the rest of these, but, well, okay, real quick, 1.6. Factor. You need to think GCF here. And what you need to think, this 4a to the 3m plus 2, there's a 4 there, right? There's also an a to the 3m times an a to the 2nd. Look at that with me real quick. You see the 4, that's obvious. A to the 3m plus 2. Well, what's the rule? If the bases are the same, you keep the base and add the exponents. Isn't 3m plus 2 3m and 2? So if you break that first term up like this, what GCF do you see? They both have a 4 out front, because 4 is a factor of 16, and a to the 3m. So we can factor out GCF of 4a to the 3m. Leaving us up front, the 4 is gone, a to the 3m is gone. We still have a to the 2nd minus, what about this one? A to the 3m is gone. 16 divided by 4 is 4. Okay, guys, algebra 1, big and bold. How do you factor a squared minus 4?
It's just a plus or minus 4.
Not a plus or minus 4.
But that's what I'm saying.
It's a plus 2 and a minus 2. Okay? Now, yes, you need to do homework for tonight, guys. That's how calculus works. Okay? Sorry. We'll work to do some cleanup here in these first few days, I promise. Your homework, it says problem set 1. It starts in the middle of the page, folks. Problem set 1. It starts on page 5. Okay? Starts problem set 1. You start here at 1. You go until you hit problem 25, which is probably on the next page. Understood? So you're looking for 25 homework problems. We'll talk more tomorrow, but do your best at it. I don't expect it to be perfect by any means. Okay? Do your best. Attempt everything. See what you can do with it. We'll talk tomorrow, okay? Give me a chance to come back and clean things up, and we'll figure it out.